So I started recording it, and today we are going to look at tunnel surveys. Engineering surveying, as we defined before, is an interesting subject, and it deals mainly with setting out for engineering works, and you'll mostly be coming across construction works. So think of the construction work for buildings, roads, railways, airports, and monitoring the same. You need to apply engineering surveying to ensure that they are constructed according to the design requirements. Even before that, you need planning for the same. So how do you come up with the maps that should be used for planning? How do you set out within tolerance, that is the maximum allowable error? How do you test the instrument you are using to ensure that it's accurate enough for the work? And how do you ensure maintenance? Roads, for example, do require what we call routine maintenance, then periodic maintenance, and what we call reconstruction or rehabilitation. Measurements from engineering surveys assist in detecting the level of need for such scheduled maintenance. Again, you need to monitor structures. Are they deforming? And if they are, when should corrective measures be taken? And this deformation is so subtle that you need engineering survey measurements to deduce, because they could be in the order of sub-millimeters in a month or in a year. Dams could be deforming on a mining site, for example, and you need measurements, periodic measurements, to detect if any built structure is going out of the designed geometry, maybe settling over time, subsidence. So we have subsidence engineering, which is critical to mining operations to ensure safety in mining areas, to monitor those dams. So deformation monitoring is also a key assignment under engineering surveying. To deliver better on this subject, it's better to share practical examples. So I'm going to share a practical example of tunnel surveying. And tunnel surveying is arguably the most demanding aspect of engineering surveying, because tunnels during final finishing works do require high levels of accuracy in the order of millimeters. So I'm giving you this example. I participated as a young graduate and engineering surveyor. This was my first assignment after graduating from university, the first professional assignment as a surveyor, and specifically a tunnel surveyor, which is part of engineering surveying. The project was 𝕊𝕦𝕣𝕧𝕖𝕪 project, which was designed to add 60 megawatts to the national grid. It is a hydropower project, but the tunnel that was going to deliver on the same was had to be constructed about 7 kilometers long. So you have to effect both horizontal control and vertical control. Horizontal control for horizontal alignment, so that the two teams excavating the tunnel from the ends would meet up accurately. Again, vertical alignment to ensure that you meet up not only accurately in terms of the horizontal alignment, but also vertically, so that the two tunnels don't bypass each other because of wrong vertical alignment. And again, they don't bypass each other because of wrong horizontal alignment. So let's go into the details of this project and see how engineering surveying techniques are coming alive from this. So Next, you'll see the uniqueness. How are tunnel surveys unique or underground surveys generally? What are the geospatial techniques you need? Now, that is just showing you how few tasks are as challenging and fascinating as to surveyors as tunnel surveys. Why? Because of the unique underground environment for tunneling. Now you don't have visible landmarks. You are just guided by the calculations that you have learned from surveying. And these calculations are the ones that are going to determine if the errors are kept to a minimum to meet the design requirements, and if you are excavating the tunnel in the right direction, horizontally and also vertically. So you see how the underground environment can be like. You need the safety gear, the helmet, your dust uniform. And you see, I was inside the tunnel here. If you are very keen, you can tell me which kind of instrument I was using here. And then also tell me whether I was using it for, I was keen on vertical alignment or horizontal alignment. So that is a good point to start from. So I want to hear from you, which instrument is that under that confined underground environment? I want to get an answer from you. So Beatrice Gujiri, what is the answer? Which instrument is it? And what was I using it for?
I think it's a level.
Correct.
And it was used for vertical alignment.
That is correct.
Yes.
Had we done, or had I presented this one to the class before?
No.
Okay. That is correct. So this is a level. It is very easy to know a level. A level doesn't have that big vertical circular section, vertical circle, or a circular section beside on the side, and a level doesn't have that freedom of movement along the vertical plane, so it won't. This telescope won't move up and down. It is fixed in the vertical plane to give you accurate vertical measurements for vertical differences in height. So that is the uniqueness of a level. A total station or a theodolite will have that vertical circle. We call it vertical circle, and it is a rather large circular part beside the telescope, and it can move up and down like this. A telescope, the telescope for theodolite and tachymeter total station, because the instruments are used for measuring vertical angles as well as horizontal angles. So for a total station or theodolite, you find that the telescope can move along the horizontal plane, that is can make that 360-degree rotation along the horizontal plane, and at the same time it can move up and down, so you can get angles of depression and angles of elevation. But for a level, the telescope is fixed in the vertical plane, and you can only rotate the instrument along the horizontal plane. This is an automatic level I was using for vertical alignment. That is to get differences in levels or in elevations, delta H, and hence, based on benchmarks, you can get what we call reduced levels in the tunnel. So you set out those vertical differences to come up with the reduced levels, which assist in slope planning. They assist in achieving the gradients designed for a particular section of the tunnel so that the water could flow downstream as designed. So let's proceed. Tunnel surveys unique, but how are they unique? So you can see I'm already giving you examples, detailed examples of how tunnel surveys are unique, distinct from other engineering surveys on the surface of the ground. So tunnel surveys are underground surveys. They take place in underground environments, or those when you are constructing those boreholes. So let's say they are underground where there are no landmarks for approximate positioning. There's dust underground, rubble, flowing water, that is underground water, poor lighting, and poor ventilation. So there must be some way of ensuring ventilation underground. You pump air into the tunnel, and that was a very energy intensive exercise underground. And we have to enter the tunnel using gas masks and helmets, compulsory for safety, helmets for safety because of rocks that may fall on you, and then gas mask are also compulsory for your safety underground. Then your safety filtering dust so that you can breathe in clean air. They require high accuracy standards for final finishing works. When you are now setting out the invert levels for the concrete to be used for alignment for based on a formwork that you have aligned as a surveyor both horizontally and vertically. Blasting and vibrations were the norm, or are the norm when we are talking of these underground works in a tunnel. And this describe control points and instrument position. So the control points that you've set inside the tunnel have to be checked regularly to ensure that they have not moved, and to tie them to the control points on the surface. So we used to run traverses regularly from the tunnel to the surface, and to ensure that the control points were still reliable enough for controlling the work underground. Again, these control points, because the tunnel is long, you won't always be waiting to run a traverse from wherever you are once you have excavated a long section to the surface. So there was the necessity of having what we call adits. So these adits are some intermediate entry points into the tunnel that can allow surveyors to go outside the tunnel and strategically tie the control points by running a traverse, the ones underground, to tie them to the surface and ensure that you are still within the designed mathematical framework for aligning this tunnel. Also, both X, Y, and Z, and Z here is the capital H because we are dealing with automatic heights for leveling. So the work had to be controlled in 3D to attain the design slope and go according to the designed directions of alignments, horizontal alignments. Again, geology was key. We had geologists on our team because these geologists were the ones to investigate the rock type and the technical requirements for reinforcement. So geologists would conduct their tests, and based on that, inform the team where we needed steel reinforcement underground and where we needed shotcrete instead of steel, and where we didn't need any interventions in terms of reinforcement because of the strength of the rocks in that section. Maybe you have granite. In other areas, you have very loose rocks that would need reinforcement with shotcrete, and others with steel plates. And those are key parts of safety underground. So this was practical daily activities within the tunnel, and I believe the same was replicated for the Northern Collector Water Tunnel from Murang'a. Now let's proceed. Overview of tunnels. Typologies. How can we classify tunnels? This is how we can classify tunnels. We can classify tunnels into rail tunnels. And by the time of putting up these notes, second tunnel was one of the longest in the world, 53.9 kilometers and 23.3 kilometers under the seabed. This one was completed in 1988 at the cost of 3.6 billion US dollars. Maybe you'll be interested what of this on the 𝕬𝕣𝕧𝕖𝕪 power tunnel, the one I worked on, the project I worked on. By the time we were completing the tunnel in, I think 2003, around there, completing the civil works, it had consumed billions of shillings, and the budget had shot up to more than 12 billion Kenya shillings. That is as at 2003. Recently, we had Gotthard-based tunnel from Zurich to Milan. The longest rail tunnel completed in 2016, but you see, it was built. The works commenced way back in 1996, so you can see how challenging tunnels can be and the amount of time they can take. Time is also a key part of the resource you need, the resources you need, and the estimate was a whole 10.3 billion US dollars, and the length more than 57 kilometers. That is a rail link through the Alps connecting Zurich to Milan. We also have this famous tunnel that is connecting Britain to France. I think I talked about it briefly in class some time back. More than 50 kilometers, but about 38 kilometers is under the sea. So you see why we need geological investigations, the geology under the seabed, and hence ensure the safety, the reinforcement you need to stop any seepage and ensure that workers can be safe underground. Such are the major breakthroughs of underground engineering works, and engineering surveys are key component of ensuring professional integrity of the works and general engineering integrity of the works for safety and meeting the accuracy requirements. So you can see even here, Gotthard-based tunnel, you see underground, this underground environment, but you can see it is well lit. So for tunnel surveys or underground surveys, you'll see need some form of artificial lighting because you can't rely on natural light. And this lighting is what will aid in executing the survey measurements, because you need to see the target, and the instrument is optical. It's an optical instrument, so you need to use light to see. You need to align, for example, this is a rail tunnel. So even the railway line here has to meet the engineering specifications. But again, how do you ensure that the tunnel is wide enough to achieve the requirements for free movement underground, because vehicles also need to transport workers underground. You need the ventilation, you need dust suppression interventions underground, and you need the safety gear. You can see here this surveyor has a helmet. What I can see is a gas mask, but you also need the same. We used to have the same. So those many years ago, you was already familiar with those gas masks. So towards this corona and the masks that we have to wear are not the first time we are using such masks as a daily routine for work. So we have tunnels that we can refer to as subways. We have road tunnels and we have water tunnels. So the 𝕊𝕦𝕣𝕧𝕖𝕪 tunnel is classified under water tunnel. It was, according to the design, I can remember 6.194 kilometers long. So that is about 6.2 kilometers. And then the Northern Collector Water Tunnel, 11.8 kilometers long from Murang'a to contain the floodwaters from Irati, Gikiji, and Maragua rivers. And it is all the way from Murang'a to Thika Dam. And you see that was the budget, 6.8 billion Kenya shillings. So you can see the 𝕊𝕦𝕣𝕧𝕖𝕪 power tunnel, though shorter, had a higher budget, more, 12 billion. That is almost twice this budget. And construction time was allocated 40 months. We also have bicycle and pedestrian tunnels. So just see some aspects of the world's longest tunnels, like this Delaware Aqueduct, all 137 kilometers long. The first ones I gave you, for example, the Gotthard Tunnel, that was a transport tunnel, rail tunnel. So it is just the longest in terms of transportation tunnels. But look at this one in the US, very long, 137 kilometers long. And what of this other water tunnel, 120 kilometers long in Finland. So you'll be able to go through this so that you can have an overview of those tunnels. So this specific project, the 𝕊𝕦𝕣𝕧𝕖𝕪 power project, whenever you have these engineering works, you must know, you must have some basics on project management. So you must know who we call the client. The client is the employer. So the client is the one contracting, the consultant and the contractor. So in this case of 𝕊𝕦𝕣𝕧𝕖𝕪 power project, some basics on project management. We had the employer or the client being KenGen, Kenya Electricity Generating Company, and the funds coming from the financier, the Japan Bank for International Cooperation, and KenGen made part of the cost. So here you can see started way back in 1999, completed in 2005. Why 2005? I talked of civil works. We completed civil works in 2003 because there are other works such as electromechanical works for the power stations to generate electricity downstream. So you need both civil works and electromechanical works. Now, the budget in dollars, that one. Who was the consultant we had during civil works? We had this consultant during civil works called Nippon Koei, also a Japanese company for civil works, and there were other consultants for the subsequent phases. The contractor, we do have what we call consortium, a plural consortia, that is bringing together different entities, so different companies to compete for the works, the contracts, and then the winning consortium, that is group of companies, is given the contract. So in this case, I was working under Konoike Construction Company, but it was within a joint venture. So this joint venture brought together Konoike. So a joint venture in this case is a consortium. Rural is consortia. So we had within that consortium, Konoike Construction Company and Vedeke Murray and Roberts. If I can remember, this was a South African company. So I was working under this joint venture with the main contractor, phase one, civil works. And civil works is where you have civil engineers as professionals, you have surveyors, as professionals, and specifically in this case, the surveyors are executing engineering surveys. So they are engineering surveyors, or specifically if you like tunnel surveyors. So that is civil works. Then quantity surveyors are also there. We also have architects there because this is a construction project, so you need them. So let's go to the next slide. The place, the geography, you must be conversant with that. So if you are going to work somewhere after your graduation and you're going to deal with mining surveys, you need to know the place, the geography of the place. So the place, for example, here was Upper Nyakach, now in what we call Kisumu County. It was in Nyando district, some 60 kilometers from Nairobi and 63 kilometers from Kisumu. The route, if you are from Nairobi, that is the route you have to follow. In engineering works, we do have what we call base camp, the employer's base camp, where the employer constructs buildings to house the consultant. The consultant in this case also called the engineer. And in this case, it was, as we saw before, not Konaika, but the Ponkoe company. So this employer's base camp, finally after the consultants have left the site, it remains a property of the employer, in this case, Kengen. So this project extended all the way from somewhere called Kolwen. Don't read it as Kolwen, it is Kolwen to Kadongo neighborhood. And for water tunnels, we must have a part we call intake. So we have intake facilities where water enters the tunnel. So you have to construct an intake weir. Again, engineering surveying is critical to aligning these intake facilities, the intake weir, so that you can have it located in the correct place, X, Y, and also vertically the Z. And you must have the gates well set out to be within the right location according to the design, so that water can enter the tunnel at the correctly designed location for intake or facilities and intake, where to control the water velocity as it enters the tunnel. So those gates should also be controlled. So there are mechanical gates, for examples, and when you don't need any more water to enter the tunnel, you close the gates. That is also true for the hydropower project at Jinja, which is using water from the River Nile. The River Nile, is an outlet of Lake Victoria. So the design specifications, that was the length. But this length, again, we have a part of the tunnel we call penstock as you go towards the power station. And you must also have a head. This head is meant to harness the water to give you the kinetic energy you need to generate the 60 megawatts. So the designed head was 197 meters, that is the total fall, delta H, and this is what you use as a variable in the equation for converting that potential energy to kinetic energy. And that kinetic energy, is what will rotate the motors and help change that mechanical energy into electrical energy as you rotate that motor. There was also the provision to have an additional power station of 20 megawatts. So the total budget was to produce a total power budget of 60 megawatts. There was also supposed to be irrigation project out of this 𝕊𝕦𝕣𝕧𝕖𝕪 power project to pave way for irrigation projects, so that once the water has been used to rotate the turbine to produce power, we would also have the water being directed for irrigation. So you can see in terms of development, it was meant to provide clean energy, clean in the sense that hydropower generation of energy is considered as part of clean development mechanism, CDM, because it doesn't produce the greenhouse gases, mainly CO2, which comes from fossil fuels. You know, electricity can be generated thermally using by burning oil or fossil fuel, and that is not a clean process because it generates, it produces greenhouse gases which warm up the planet, such as carbon dioxide, methane, and oxides of nitrogen. So let's proceed. 𝕊𝕦𝕟𝕟𝕣𝕧𝕖𝕪 tunnel, those were the specs for engineering work. So you must have what you call as work adits, which I talked about before. The kind of tunnel we had in this case is called headrest tunnel. It was designed to have diameters that we'll see and gradients that we'll also see. Downstream, what you call a surge tank. What is the role of the surge tank? The surge tank is meant to reduce the excess hydrostatic pressure built up as the water has traveled that long distance of more than 6 kilometers. So it comes with a lot of kinetic energy. So the surge tank is to offset that excess hydrostatic pressure, that surge. And this surge tank again needed surveyors to be continuously on site to ensure that it would be constructed according to the design with a diameter of 14 meters and a depth of 36.8 meters and to be erected vertically. So that again requires the application of engineering surveys to set it out correctly and attain the vertical alignment required. Again, engineering surveys for construction of the houses, the offices, powerhouse building, and outlet channel. So once the water has been used for power generation, there must be an outlet channel. That outlet channel has to be surveyed so that it can attain the correct horizontal alignment and the correct slope for draining the water downstream. So the second phase is hydromechanical works. So you talk of the intake, the gates on the weir, irrigation outlet, generation equipment, switch gear, transmission lines, and substations. Most of these works were accomplished in the second phase of the project. So look at the design specifications now. Total length. Straights means the straight sections, as we saw before. We have straights and curves. The curves we had in the tunnel, a curved section which had a radius of 400 meters according to the design, curve length of that, intersection angle of that, tangent length of that. Slope for that section was designed to be 1 in 1,000. So you interpret that one to mean dy over dx is equal to 1 over 1,000. So when you have an horizontal displacement of 1,000 meters, the vertical difference in height from the starting point is 1 meter. Or if you have horizontal difference of 1,000 millimeters, the drop is 1 millimeter downstream. We also had another section with a curve designed to have a radius of 200 meters, and that curve length, intersection angle of that one. This intersection angle we talked about before is equal to the angle at the center. So this is your theta. And you know very well that if this is your theta, then that delta, that angle delta, which you drew very well, is theta over 2. And so the tangent length you can easily calculate as r tan delta. So if you take the radius 200 and you multiply by the tangent over half of the intersection angle, you should be able to get 118.558 meters as your answer. That curved section with a radius of 200 meters was designed to have a slope of 1 in 300.5. So the slope there was steeper than the slope for the section with a curved radius of 100 meters. But we also had a straight section. So these curves were joining the straights. The straight sections had a descent gradient of 1 in 1000 as well. So I want you very quickly in the next 2 or 3 minutes, verify that these curve lengths are correct according to the formula we derived in class. So in the next 3 minutes, do that from your calculators and confirm. If there's a difference, let me know. So that is what you are doing in the next 3 minutes. Then we proceed. Musimi, are you saying something? Your microphone is on. Can someone now tell us what your findings are? If the relationship between the tangent length for the section of the tunnel, the intersection angle of the, which is equal to the angle at the center, and the curve length, can you let me know if you are getting those answers according to the formula we derived last time? Someone to volunteer and talk? And now, Candia, what do you get? Okay, I'll proceed because it seems no one is engaging. So those were the slopes and spans. And for final finishing works, up to 1 millimeter tolerance allowed, only 1 millimeter tolerance allowed, very accurate. This is how you can prove mathematically y for a given radius and tangential angle delta. We are using a given length of formwork. So if you look at the formwork lengths, where we had a radius of 400 meters, the formwork length, if you calculate, you get 4.5 meters. That is what we are using. So this is just part of the justification. Where we had a radius of 200 meters, the formwork length 3 meters. So the formwork we are using for those sections are to come from the calculations, and you see those calculations are based on curve geometry because they are curved sections, and curve geometry is something we have already done together in class. There's no way you can execute engineering surveys without curve geometry. Then the philosophy again is that if you can keep the linear distances and angular measurements for directions are level to within a millimeter accuracy in a uniform reference system, the correct horizontal and vertical alignments of the tunnel can be achieved despite the difficult underground work environments. For example, you have narrow sight lines with little room for maneuver. You have no landmarks for visual approximation, and you have to save time by excavating from both ends to meet up in between. A fundamental philosophy in tunneling works. So that is just a summary of how surveying was critical to the project. And when we talk of property surveys for land acquisition and compensation, you need to know the size of land parcels and the beacons. So you see, it is surveying having a major role to play here. So when we talk of land and compensation, you know, now we are talking of land rights, hence the application of what we call cadastral surveys, which we saw is a branch of land surveying. And deformation monitoring, you also need that for safety. Now, how are we going about the drilling works? Look at this thing we call drilling jumbo at work during excavation, because you need to excavate fast, not very accurately, but just to provide room for transporting materials and surveyors to get room to carry out more accurate alignment works. Reinforcing steel formwork inside the tunnel. Again, you see how it used to look like. I said it is a headrest tunnel, which is circular in shape. So even that formwork for construction must be circular. It must be set out to be well aligned horizontally as a horizontal cylinder with the correct diameter and correct slope. And based on that, those steel formworks are mounted on it. You have to ensure that you construct that steel formwork when the steel form when the formwork you are using has been aligned by the surveyors both vertically and horizontally, so that upon removing that formwork, you remain with that steel formwork which is accurate in terms of diameter, the direction, that is the bearing, and also the slope. It has to slope because the tunnel will also be sloping according to the design given. So we had to use reinforcing steel bars and to survey them. And look at this, it doesn't have a major dam associated with it, but it relies on the river flow, only using a storage capacity at the intake, diverting water through that 6.2 kilometer long tunnel. So these are intake facilities where water enters the tunnel, and you can see these walls, these vertical pillars have to be surveyed during construction. Then you have to inspect the address tunnel. Now you cannot see the steel formwork anymore because it is now inside. The formwork is inside, and the final concrete finishing is taking up the shape that is designed. So this is what we are saying. The diameter should be 4.2 meters for this tunnel as it was designed. And you can see even after finishing with concrete, still some groundwater is flowing here. Groundwater is a permanent feature in tunnels, so you have to engage the watering. The watering is a key part of this assignment, the watering mechanisms. So surveyors also have to come after the work has been finished like this. You take some measurements at specific points in the tunnel to check if the invert levels here, according to the ℔, are correct. So you have to know the ℔ where you are. Take the level. Is the level correct there? If it is off, it is by how many millimeters? Is it beyond tolerance? If it is beyond tolerance, you have to reconstruct that section and have it redone to attain the correct slope. Again, the bearing, is it going in the right direction? So invert level of finished tunnel section, reinforced steel lining is inside. Surge tank, which I said the depth is more than 36 meters. This is now at the downstream end. So during excavation, laser techniques are key. Why laser? Because when you are underground, a laser beam gives you a very sharp line of sight. So if you have a laser, you need laser machines, and this beam will not just be beaming anyhow. A surveyor has to set it up. So you have to set up the laser equipment such that it is giving you a line of sight for reference, and this laser beam must be surveyed to have the slope that is designed according to the slope of the section being constructed or excavated. So the beam itself should be sloping, and the beam itself should be going in the right direction. So the beam also needs both vertical and horizontal alignment. So that beam must be a line of a deliberate line that is set up by surveyors to attain the mathematical equation that is accurate according to the design works. Because, you know, as a straight line, it has a mathematical equation, and that mathematical equation has to ensure that it is going in the right direction and attaining the right slope, or else you'll be excavating in the wrong direction, horizontally, and in the wrong direction, vertically, going either too deep or remaining too shallow or going up too much. So excavation radius, you see it is more than the radius for the finished tunnel. The radius for the finished tunnel, 2.1 meter, because diameter is 4.2 meters. But now for the excavation radius, you need to go beyond that so that you have room for maneuver as you go for final finishing works. Straight sections, you see even for straight sections, we had laser beams being used, two parallel beams, 2.2 meters apart. And as I've said, the beams have to be aligned vertically as well at targets to slope at the design gradient of the tunnel of the section being excavated, and survey demarcations and checking within tolerance of 5 to 10 centimeters, and coordinates used for accurate checks later. So what we are saying here is that during excavation, you can allow this plus minus 5 to 10 centimeters because it is excavation, but during final finishing works, we don't talk of centimeter allowances, it is millimeter. You have to be accurate within millimeter. So excavation of curved sections, now you can't use, for curved sections, you cannot use two laser beams. You only use one laser beam, one at a time, and you do your calculations as a surveyor to get the offsets right and guide the team how to excavate the tunnel such that it curves and traces the circle, the circular geometry in the design. So this example is for a straight section. You can see the laser beams, this one and this one, and then this central line, the blue one, which is coinciding with the center line. It is parallel to the center line, and you know it is above the ground surface, above the ground surface. So it is an imaginary line, but it has to be set out in such a way that it follows the design center line of the tunnel, that is vertically above it or parallel to it. And that is why we call it the spring line, the latitudinal axis. Yeah, this one is what we call the spring line. It is perpendicular to the spring line. This black line is the latitudinal axis of the tunnel, and we call it the spring line. Yeah, it is indicated here, spring line. So as a surveyor, you have to ensure that if these are the targets, you have to know the XY locations of these targets. You set out that at a given chainage, and this one must be diametrically opposite it, this other side. So if you have that laser machine here, after doing your calculations, you get the bearing. So based on the bearing, you have to set up the bearing and ensure that it goes in the right direction. And at this chainage, you have another target, and check if you go to that target. And that also brings about the challenge of vertical alignment, because at this chainage, you have to know what is the elevation, the design elevation. And so based on that, where should this laser beam pass to attain the gradient? Because if this is downstream, this part is downstream, then the elevation of this point must be higher than the elevation of this one. They must have a difference that will give you the gradient you need for this section according to the design. So once you have set up that, ensure that the laser beam gets the right direction and gradient and passes through this target point, through your vertical and horizontal alignment, and then in between you have a check. So based on the chainage of this point, you know the elevation for this point based on the design requirements, and this one acts as a check in the sense that if from here to here is correct, then when you align these ones independently, the beam will be passing through this target without you forcing it to pass through it. So this is also practical implementation of one of the principles in surveying, which we call having a check. You must have a check always for your work. So this one is not anything different. It is just the projection onto the floor plane of what we saw here. So when you project, you know, this, as I said, this plane is not on the ground. It is not on the surface of the tunnel, the bottom of the tunnel. It is imaginary along the latitudinal axis. Now I'm projecting it onto the floor. Something you have done in engineering drawing. You can see in 3D, that is what we call spatial skills, spatial thinking. So when you project it onto the floor, you will come up with something like this. Not very hard. Not very hard to see. Okay. Now, curved section, you now have one laser beam. Again, you have to know the curved section, the specifics for the curved section. Once you have got those parameters you need for the curve, as a surveyor, now based on changes, design parameters, you should be able to tell the people that when you are here, what is the offset to the imaginary center line of the tunnel. So you give this offset, that distance has to be measured from the laser beam, and vertically downwards you mark on the floor of the tunnel where it should be. For example, for this straight section, the straight that this curve is joining, you know, this curve is joining one straight section to the left and another straight section towards the right here. So this straight at a bearing of 307 degrees, 42 minutes, 42 seconds. And you need that in order to carry out your calculations as a surveyor. So with this laser beam, these offsets are key from the laser beam to the center here. From here, if there is a change, you are interested in here to the center. And then from this point that I've used as an example, from this point Y on the laser beam to the center. So by marking out with spray paint, the surveyor is giving discrete points that when connected will trace out this curve, the center line of the tunnel. And because you know how wide the tunnel is from the center line, you give an offset. So if here we have 4.2 meters from one end to the other, you know very well that from this center line, you need an offset of 2.1 meter both sides. And that is how you end up guiding the team in the tunnel using surveying techniques. So this is just an example from the technical report, how with this example, as a surveyor was able to determine the offset AY, because you need to show where the center line is. What you have is the laser beam. You don't see the center line. As a surveyor, you're the one to place that center line where it is based on the mathematical calculations. And here the example used here is for a radius of 200 meters. The curved section with a radius of 200 meters. So just basic maths using the equations of straight lines. You also know the equation of a circle as someone who has done engineering. You see that equation I gave you in class, 2r sine delta for the chord length. So all those are practically applied. Without them, you cannot have these tunnels. So they are not just for academic interest, they are practically applied out here. So you see how long the calculation can be. So as a surveyor, you must do the calculation before you go to the tunnel. So you plan ahead of time. Before you go to the tunnel, you have your calculations right, so that you know at that change what you'll be giving the people as the offset so that work can proceed. So this is just an example of how long it can take to calculate that offset AY. It can take this long. So let me see, because this one was meant to be a rather short session on a Friday. I want us to wind up, because most of these, once you have got these details, you'll be able to understand very well. So there are excavation deficiencies. This dotted line is the design, but when you are excavating, because of the geology, because of unavoidable errors, there are underbreaks. So this is an underbreak and this is an overbreak. So there's a way you have to measure those from the spring line as a surveyor, so that you give the workers how much underbreak this one is. Maybe if it is 3 centimeters, we write with 3.3, so that additional blasting should be done here, or excavation, to get enough room. This is for excavation, not the final finishing, just excavation. And here, how much should be filled here. And those ones form the basis for construction costs. And the contractor uses those to make any additional claims, because these underbreaks and overbreaks come with their own costs. Clearance works. Yeah, this is just an example of how you can measure the overbreaks and underbreaks. So if the radius you need is 2.4, but what you have measured is R, then R minus 2.4 is X, where X is underbreak if it is negative, and overbreak if it is positive. And how are we doing that? From the spring line, which you determine, and then you hold a string, 2 people holding a string at both sides of the tunnel to define the streamline. Now with a leveling staff, you just ensure that the bottom of the leveling staff is touching the surface of the excavated tunnel. So at discrete points, you take the measurements, and by using this formula, for example, if you needed excavation clearance of radius 2.4 meters, then whatever you measure is R minus 2.4. If it is negative, you know it is an underbreak. If it is positive, it is an overbreak. Then you indicate as a surveyor at those points, so that they can help with preparing enough room for excavation and attaining some fairly uniform clearance for further works. So reinforced concrete lining, removal of underbreaks, inventorying. These ones are now easy. We also have what we call blinding. So you have some concrete on the floor to increase the bearing capacity, and also to ensure that when you have that, the flow of the tunnel can now be more conducive for setting out works by the surveyor, because you also need some fairly firm ground for setting up your equipment, and also for using concrete nails. And those concrete nails, you know, are what you use inside the tunnel to establish temporary control points. So those concrete nails also need a firm floor. And as a surveyor, you have to know their coordinates. You have to set them out in such a way that their coordinates are well known. And based on them, you can guide the work underground, both by horizontal alignment and vertical alignment. Spray paint your normal companion inside a tunnel, because spray paint is very visible, and you demarcate where the concrete lining should reach using such spray paint inside a tunnel. So spray. Hello, can you get me? Who can get me? Hello.
Yes, we can get you.
Hear me?
Yeah, we can hear you, sir.
So let me just finish. So we are saying you need spray paints. And we had shown this one's reinforcement, casting concrete. I want us to end here where I'm showing a cross section. So you see, this is the tunnel. When you are still excavating, this one was the line. You see how irregular it is, and that is where the tolerance we set for this kind of work excavation is just 5 to 10 centimeters to be practical. And then look at this. What is this now? This is now the framework of reinforcing bars, the steel bars we saw. And then you see the all of this is concrete lining, the all of this. And then final finishing work, you finally attain the diameter of 4,200 meters. It should be 4,200 millimeters. Yeah, 4,200 millimeters. 1 m is remaining there because it's 4.2 meter diameter. And then this one was also key. The design was to have this from the blinding. You have another 300 millimeter of concrete to reach the invert level here. So that cross section is giving a summary of excavation line from the beginning, then reinforcing bars, then filling in with concrete, and finally attaining this circular section of the headrest tunnel. So I want us to end here. Let's get any questions. We'll go through it next time because it is long. It is not short. So any questions before we close for today? Let's get the questions coming. Any question, any question? Okay, that is the poll. The poll is there. Please, before you leave, do the evaluation.